Let us look at the another method of solving the question of the previous lecture. The question which I had discussed in the previous lecture is like this. It says a matrix B, a matrix capital B of order n cross n is of the form lambda A, where lambda is a scalar and A has unit elements everywhere except in the diagonal, which has elements mu. Determine lambda and mu so that B may be orthogonal. Okay, so it is given to us that B is orthogonal and we have to determine lambda and mu. Value of lambda and value of mu we have to determine, and B is orthogonal, it is given to us, and along with that this entire condition from here till here it is given to us. Okay, so I have already discussed the first method of solving this problem. Now I am going to discuss the second method of solving this problem in this lecture. The value of lambda and the value of mu which we will get from the second method, that will also be the same as that we got from the first method. Okay, whatever value of mu and lambda we get from the first method, the same value of mu and lambda we will get by the second method as well. Okay, so it is given to us that capital B is equal to lambda times capital A. It is given to us this particular thing. Now capital B is equal to lambda written as it is. According to the given question, capital A can be written like this, that is mu at the diagonals, and everywhere except diagonals it is the 1. So over here 1 1 1 1 1 1 1 up to here, and the order is n cross n. The order is n cross n. It means that 1 2 3 4 n rows, n number of rows and n number of columns. Okay, 1 2 3 4 like that n columns, and 1 2 3 4 like that n rows. Okay, so this is the value of capital B matrix lambda times this particular matrix, where there is mu at the diagonals and off diagonal elements, all the off diagonal elements are equal to 1. Okay, or the non diagonal elements are equal to 1. Okay, now it is given that capital B is orthogonal matrix. So we already know one condition of orthogonal matrix. What is that condition? We know that the sum of square of each element in a row is equal to 1. The sum of square of each element in a row is equal to 1 in an orthogonal matrix. Let me give you one example. Suppose there is a matrix alpha, beta, gamma, okay, delta, kappa, okay, alpha, beta, gamma, delta, kappa, alpha, okay, and we have A, B, C. Okay, this is the matrix which we have with us. Let us replace this alpha with something else. Okay, let us replace it with something else. So let us replace it with sigma. Okay, let us replace it with sigma. Now this is the matrix. Then if it is orthogonal, what is the condition satisfied? The sum of the square of each element in a row is equal to 1. Okay, sum of the square of each element in a row is 1. So alpha square plus beta square plus gamma square will be equal to 1. Okay, so this first row covered. Then what about second row? Delta square plus kappa square, okay, plus sigma square, that will also be equal to 1. Okay, so second row covered. And similarly third row, what will it be equal to? A square plus B square plus C square, that will also be equal to 1. Okay, this is the third row covered. Okay, now what is the condition? This condition has been satisfied. Now let us consider the same matrix once again, this matrix itself. But right now we are considering, let us rewrite this particular matrix. So that you understand it better. Okay, alpha, beta, gamma, delta, kappa, sigma, okay, and A, B, C. So I rewrote the same matrix. Now let us erase this. So the first condition already done. Alpha square plus beta square plus gamma square equal to 1. Delta square plus kappa square plus sigma square equal to 1. A square plus B square plus C square equal to 1. Okay, this is the first condition which is satisfied if this matrix is orthogonal. Now what is the second condition that must be satisfied? The sum of the product of elements of any two rows. Okay, so sum of these two elements multiplied by these two elements. Okay, so what will be the thing? The thing will be that alpha delta plus beta kappa. Okay, first and second row, I am considering first and second row. Okay, so gamma sigma, this product should be equal to 0. So which rows are covered? These rows and this row and this row are already covered. This particular row means first and second row are already covered. So this is the condition which they must satisfy. So first row and second row cover. Now let us talk about second row and third row. Let us talk about second row and third row. So let us do. So A delta plus B kappa, okay, A delta plus B kappa plus C sigma, that should be equal to 0. So first and yes, second and third row are covered. Okay, this was the product you got when you considered first and second row. This was the product you got when you considered the second and third row. And now we will consider the first and third row. We will consider the first and third row. So alpha A plus beta B, okay, plus gamma C, that is equal to what? That is equal to 0. Okay, so this is the condition. So there we got how many equations in total? In total we got 6 equations. Out of those 6 equations, 3 equations satisfied this number 1 condition and the other 3 equations satisfied this number 2 condition. Okay, so let us apply these conditions over this particular matrix and understand it in a better way. So this is the matrix. Now B is orthogonal. So the sum of the square of each element in a row should be equal to 1. So this element is square plus this element is square plus this element is square up to the last element is square. That should be equal to 1. This element is square plus this element is square plus this element is square up to the last element, that should also be equal to 1. Okay. And the other condition is that mu into 1 plus 1 into mu plus 1 into 1 plus 1 into 1 up to the last element, that should be equal to 0. That should be equal to 0. Okay, so sum of the product of elements of any two, sum of the products of elements of any two of any two rows is equal to 0. Okay, sum of the product of elements of any two rows is equal to 0. So what are the equations that we get from here? So let us write the equations. Let us write the equation. So consider the first row. Consider the first row. So the equation will be mu square plus 1 square plus 1 square dot 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 dot, okay, plus 1 square. Now there are total n elements. Okay, so this will be in turn equal to mu square plus 1 plus, because 1 square is equal to 1, so 1 plus 1 plus 1 up to the last element. So how many elements are over here? Over here n minus 2 elements, n minus 1 elements are there. Over here n minus 1 elements are there. So it will be mu square plus n minus 1. Mu square plus n minus 1 is equal to what? Mu square plus n minus 1 is equal to, it is equal to 1. Okay, mu square plus n minus 1 is equal to 1. This is the first equation which you get. Now if you try to apply this condition over this second row, third row and up to the last row, you will get the same equation. You will get the same equation. Okay, so from the first condition we got this particular equation, mu square plus n minus 1 is equal to 1. Okay, so let us see. So mu square plus n minus 1 is equal to, and lambda square is also there, obviously lambda square is also there, which I forgot to tell you, because this lambda is outside, right? So it will get multiplied with each of these elements. So obviously the equation, the first equation which we will get, it will be like this: lambda square into mu square plus n minus 1 is equal to lambda square multiplied by mu square plus n minus 1 is equal to 1. This is the first equation which we will get from here. Now let us try to evaluate the second equation. So the second equation, this element will get multiplied with this element, then this element will get multiplied by this, then this element with this, up to the last, this element with this, and we will add these elements. So mu into 1 will be equal to mu, mu into 1 will be equal to mu, plus 1 into 1 will be equal to 1, and so on and so forth up to the last element. It will be equal to 1 into 1 is equal to 1. Okay, and obviously lambda is outside this particular thing, so this complete thing will be multiplied by lambda square. Okay, this complete thing will be multiplied by lambda square, because this lambda will get multiplied with this row also, and this lambda will get multiplied with this particular row also. Okay, as it will get multiplied with both the rows, when you will take the product, lambda square will come out as common. Lambda square will come out as common when you take the product. Okay, So how many elements are from here till here? It is n minus 2 elements. It is n minus 2 elements. Why? Because from here till here we have n elements. Because there are n columns. Because there are n columns. There are n columns. So these are n elements. But 2 elements are mu. 2 elements of them are mu. So the rest of the one when they will get added, it will give n minus 2. So this particular thing gives n minus 2. So what is the second equation we get? It is lambda square multiplied by 2 mu plus n minus 2. Okay, should be equal to what? It should be equal to 0. This is the second equation. So did you get this equation? Yes, we get this equation. So have a look. Okay, so this is the second equation following the second condition, and this is the first equation following the first condition. Okay, so we have successfully written these things. Okay, so it has been explained over here. You can have a look. I am not going to discuss this and this because I have already discussed this. Okay, so this is equation 1, this is equation 2. Now if you remember the previous lecture, what will happen? These are the same two equations which we got in the previous lecture. In the previous lecture we were discussing the same problem. Same problem was being discussed. But the difference? The difference was that in the previous lecture we were discussing different method, and in this lecture we are discussing a shortcut method. This is the difference. So these are the same two elements which we got in the previous lecture. So we have already solved these two equations in the previous lecture. After you solve these two equations, what will you get? So if you want to have a look how to solve these two equations, then certainly you should have a look at the previous lectures. Okay, so solving this equation 1 and 2, you get mu is equal to this and lambda is equal to this. Mu is equal to this and lambda is equal to this. When you solve this equation and this equation, mu is equal to 1 minus n by 2, lambda is equal to plus minus 2 by n. And how to solve this equation and this equation, already told in the previous lecture. How to solve these two equations, that is how to solve this equation 1 and how to solve this equation 2. There are two unknowns and two equations. So how to solve this set of equations 1 and 2, I have already discussed in the previous lectures. From there I am directly writing the result. Mu is equal to this, lambda is equal to this, because this is the same set of equation which we got when we solved by another method. Okay, so when we change the method, even the same set of equations are obtained. When we change the method of solving the question, the same set of equations are once again obtained. Okay, so this is the thing. Now from here onwards we will study in the next class. And from up to here we have already covered. Thank you very much.